So if you recall, we were talking about, and last time we were talking about the Clifford algebras. Hopefully that made sense. But a few weeks ago, we were talking about some of the work that Mike and I have been doing on just looking at the ZF axioms and seeing what's required of the container entities to give reasonable interpretations for those axioms, or when those axioms have to bend. And you know, we considered the element of relation, and now what we're looking at next is the there exists and for all. And the reason that's important is because if you go over the ZF axioms, all of them make liberal use of the there exists and for all quantifiers. And so the main question is what interpretation can we give those, and you know, and therefore what structure must be around in the container to support that. So there's a traditional categorical interpretation. Let's see if I can recover it. Hang on a second. Okay, so now there exists, and when you're talking categorically, you're given, you want to make this work with morphisms as well. So there's an extra parameter here, which is some morphism, say F. So I'll put that here, and that's typically subscripted. Oh, but put the X in and then subscripted. Okay, I'll see if I can get this right. Typically, this is going to be some Y in, so we're thinking about this from that perspective. So it's going to be such that F of X equals Y. Now, and then that there exists is going to be, I think this is going to be, let's see if I get this right. Implies X in A. So I think that's there exists, and then for all is the other way around. Hopefully I've got this right. I might have these backwards. Oops. Hello. There we go. And then this is going to be and. I think this is right. It doesn't matter too terribly much. I might have them backwards, but so F is going from A to B. And this is kind of the standard set builder notation interpretation. I can look this up to make sure I haven't got them backwards, but it doesn't matter so much. The main idea is that we're going to, we want these curly braces to represent a kind of accumulation, right? So this is going to be a sum. This is going to be a multiplier. So this is going to give us some value. So just to keep in the back of your mind, the kind of structure that we're starting out considering is quantile valued relations. So let me just say a little bit about what those are. So a quantile Q is going to have, so it's some set together with two operations, a join, which I'll write as a wedge, and a tensor, and some unit, which I'll call K. And the tensor and joins distribute. So they distribute over each other. And then when we're modeling linear logics, you're going to have an additional operation perp, which is going to be a kind of negation, but it's a negation with respect to the tensor as opposed to with respect to the join. So when you're using typical Boolean logic, then the tensor and the meet coincide, the tensor and the join coincide, and your negation is with respect to the wedge. So you can kind of get a sense of what that lattice looks like, right? That's just an ordinary Boolean lattice. But another model would be the power set of the set of sequences of some set. So you have some set of generators, you take all the words over those generators, and then you take the power set over that. Then tensor can at the element level is just concatenation, and at the set level is you lift it pointwise. Hopefully that makes sense in terms of the data structure that we're considering. Does that make sense?
I think yes.
Okay, all right. So that's our quantile, and now we're gonna consider. So given some set X, we'll consider relations on X, which are Q valued, right? So if we have some relation, say R on X, then what we're saying is that R of X and X prime drawn from X is going to be equal to some Q. Does that make sense? So instead of true or false, right, we're now giving so normally relations on X would be, X and X prime would be either true or false. Now what we're saying is how true or how false that is, right? The Q is giving you a measure. And so now this Y element of B can be interpreted in that light. We're going to give a Q here, which is how much Y is in B. And then we're going to interpret this as a kind of multiplication, right? And so this equality relation we want to interpret as again as a kind of Q thing. So this is going to be some Q. Then you need you would need to interpret the implies. So before we interpret the implies, let's consider the and, right? So so here again we'll get a Q gadget, and here this will be this will be some other. So we sorry, A and B are both Q gadgets. So this is going to be an element of Q as well. So we're fixing Q. And so this will be an element of Q as well. And now we can interpret the and as the dual of the meet, sorry, of the join, which is a meet. So this becomes some element, say Q 0, or let's say Q sub F, and meet, and this is going to be, let's say, Q sub A, and this is Q sub B, right? And then this is the sum. So we're going to interpret then this as some sum of Q sub B times, so we're going to use the tensor for that. So I'll put the tensor in now. And then this is going to be Q sub F. And this is going to be the meet. Let's see, do I have meets? Yes, I do. There's my meet. And then Q sub A. Okay, so now I can then, we can do a subscript.
So our intuition about elements of the set is not really good here. Like we have some elements somewhere.
It's how what we're saying is this is no longer true or false, but a qualified, or in fact not even just qualified. It's a measured. So think of this as a generalization of fuzzy. Right. So when when you have a fuzzy set, you have some confidence that the thing is in the set. And here for the quantile relations, we're saying that the elements of the quantile give you just how much the thing is in the set, or how much an element is related to another element, and therefore we can lift this this quantification up to also provide a how much.
And when you say how much, are you saying this because you're thinking in these terms, like lower and more and less?
Something like that. Yeah, right. So there's a lattice involved. So there's a partial order.
Okay.
Yeah, there's a partial, and so this is giving you a measure of how true this sorry, so you'll need a you'll need a formula, but this is the basic shape of it as well. So that's the idea, is that we're and the nice thing is that then this interpretation says that whatever our structure has to be, it has to support the sum, it has to support the tensor, and it has to support the meet. All right, so quantale is really minimal in order to do that, right? So I think I've got these backwards. I think this one is the for all. And this is, oops. This is the for all. And this is the there exists. So so in general, we can do there exists, but the for all is going to require an interpretation of implies. Now, it turns out that there are two kinds of implies, right? One is dual to the meat. So then you would have an let me just spell it all out rather than stumble over the words. There's another one of these. And there's another one of those. And this was something that's always been bothering me about linear logic that no one has ever talked about. Okay, so this should be the lollipop. Do I have it? Looks like I don't have the lollipop. All right, I'm going to spell it this way. Okay, that's the linear lolly. And then this one is the and this one is the tensor. And now let's call this, so that's the normal one. And let's just give this a superscript L for the fact that it's linear. And this is really what I wanted to talk about. And then this one. Okay. So this is the point. The quantifiers are typically just giant ors or ands, right? This is really just a giant and, right? You're just making sure that every one of them is every one of the things you're trying to check, every one of the cases you're trying to check is true. Well, let me, without looking at the formulae, because the categorical formulation is a little bit counterintuitive. When you think about there exists, right, what you're saying is for all of the possible interpretations of X, I can find at least one, right? So that's a giant or, right? And for all says for all of the possible interpretations of X, all of them, right? So that's a giant and. But now when you turn that categorically, where that shows up is here versus here. And there are two kinds of implication, right? There's an implication that comes from the wedge, and there's an implication that comes from the tensor, right? So when you move to linear logic, that giant and could come from the additive side of the logic, or it could come from the multiplicative side of the logic. So that's what I'm on about here, is that there should be additive quantifiers and multiplicative quantifiers. And so that's something that's been missing in the accounts of linear logic that I've seen. Like if you go look up linear logic that has quantifiers, I've never seen the 4 different quantifiers, but they should be there. And this is beginning to expose that structure, right? And so in either of these cases, you must have an implication built in. So you have to have either an arrow or a lollipop built in, or you have to have, and that would be the intuitionistic case, or you have to have a negation. And in this case, you have to have a negation that makes sense with the wedge. And in this case, you have to have a negation that makes sense with the tensor. And then once you have those, right, so that gives you kind of a minimal structure that you can impose on your collection in order to give this kind of interpretation for the for-alls. So in the case of the linear one, it's going to be exactly the same, except where you have this, you'll have a lollipop, right? And in the case here, you'll have the arrow, right? So this is completely it's polymorphic. It's as if these take these operations as parameters, right? So these definitions are parametric in these operations, and as a result, you get the different kinds of quantifiers. And then the next step is to go back to the ZF axioms. So I think they're here. Yeah, the next step is to go back to the ZF axioms and see. So you'll see what I mean, right? There they are. And they make liberal use of for all, and there exists. So I don't think there's a single one of them that doesn't use both quantify. This extensionality uses only the for all. All the others use some admixture of them. But what hasn't been looked at is what you get if you use the linear versions of these, right? So that will give you different kinds of mathematics if you use the linear versions of these. So we want to look at the different variations of these axioms, both from a formal perspective and from an intuitive perspective, where we're looking at whether you're using the additive versus the multiplicative versions of the quantifiers, and then having sort of rung those changes, then we can get a feel for other kinds of collections. But this is now the basic program. So we sort of understand what it means to. So we're changing these kinds of predicates, right? So these kinds of predicates are no longer Boolean valued, and these kinds of predicates are no longer Boolean valued. So when you say, for example, not, you also have to give an interpretation of that, right? So there has to be some kind of negation, right? Which is, for example, in the terms of the quantale, that could either be so just to be clear, the negation that is with the wedge is an additive kind of negation. So if you want to reach for a metaphor or an analogy, it's going to be like minus. Whereas this is going to be like the negation for the tensor is going to be like division, right? So this is going to be like subtraction. This is going to be like division. So then when we go here, there we go. When we go here, when we look at this, we want to understand whether we're taking the additive inverse, like taking the minus of the element from Q, or the multiplicative inverse, taking the reciprocal of the element of Q. Right. So these are the kinds of calculations and sort of thinking through that we have to do next. So hopefully that makes sense. Any questions?
It just means that you want to use all four of them. I mean that they can be mixed together, right?
They can all be mixed together. It's not so much that I want to use all four. It's just that we want to be careful when we're thinking about these what the consequences are in terms of the kind of math that you get, you know, by changing these axioms.
I see.
Yeah. So, you know, we change these, you get new math. This is literally the foundation of math, right? So when we as we begin to, so what we're saying is that there's this kind of interplay between the logic that you use to specify the structure, the core data structure that you're going to build math on, and the core. So those two things are intertwined, is what we're saying. So if you change the core data structure, you're going to change these things, which is going to inform, like it's going to give you a different logic, right? And you just want to make sure that the logic that you use to formalize your data structure matches with your data structure. And once you have that nailed down, that gives you a notion of comprehension on top of which you can extend to build out. Basically, you end up building a distributive law. So it's a technique for forcing the distributive law from the ground up. Is really, that's one way to think about it. But anyway, so this is kind of this is the work that we've been doing, is carefully checking out the structure of the quantifiers, making sure that, you know, we have enough structure in our collection to be able to give interpretations, and then going back to this and seeing how this impacts the axioms. That's the work that we've been up to for the last few weeks. Any other questions?
If this means that depending on how we are interpreting this result of for all and exists, that we will end up with the final result of our logic with the same type of results.
Can you
so
ask?
if we have a true false, like really precise result for in the end, we will have this kind of results in our logic.
Yeah, I mean, basically what we're saying is that your predicates and your formulae all have to talk about the same thing. If they give true, false, you can think of true. Think about it like seeing in color, right? True and false is a world of black and white. And when you go to the quantalic world, you can now see in color, right? And so these predicates will be valued in a color, right? And the formulae will be valued in color. So that's what we're saying. So it's actually richer information. It's more information.
Yeah, we can choose what kind of logic we want, right?
Yes, that's the idea. It's like, so the logic is going to go hand in hand with the data structure. Okay, so that's the idea, is that what's kind of hidden here, this is really just telling you how sets work. But the fact is that you need both to go together. The only reason these formula make sense at all is because you have sets in mind to begin with. These formulae make sense that you can build models of them because you're interpreting them in terms of sets, right? So if you move off of sets onto some other kind of data structure, like a linear data structure, then not only will you know, these formula change to, you need the formulae to change in order to capture the kind of data structure you're talking about. but it's also the case that the formulae themselves may change, right? So that instead of an arrow, you have a lollipop, and instead of a meat here, you know, a carrot. Instead of a carrot, you have a tensor. You have the O times symbol. So those are things that are that will change, that will shift, and so far all of the like the work that Shirahata, I think is his name, did on linear set theories. He's trying to be super conservative about how he changes this, which is a good thing. It's a good sense, but no one seems to have actually like said, well, what if we actually just change the data structure? Right. And so that's what we're doing, is we're providing a way to make sense of how much of the data structure you can change as you move to different logics, right? So there's this logic data structure correspondence, and once you've worked that out, then you'll get axioms in that logic that basically it comes down to, you know, the axioms in the logic that pin down the data structure that is the core model of the logic. So there's a kind of, you know, there's a circularity there, right? That's present here, but just has never been made. At least in my education, that circularity was never made clear to me. It's only when I've been looking at ZF again that I realized, oh, that circularity is there, right? And so just figuring out the circularity is and how to make it rational or sane and not an endless loop is part of what we've been doing. But there's also a bunch of there are a bunch of constraints, right? So the language that you want here, as you know, it has to be consistent with the implied data structure. So, for example, you know, if you have a logic where your core data structure is row, that's perfectly reasonable, right? Your core data structure is row, right? Then the namespace logic is what you would be able to express here. And then what you'd use is namespace logic to spell out all the row terms, right? All the kinds of legal row terms that you are willing to entertain as data structure elements, right? That would give you an example of another way to run this. Yeah. Anyway, it's a lot of work because, and most of the work is like unburdening my mind of years and years and years of you know, how this, you know, how math is supposed to work. and saying only what, you know, what must be the case in order to be consistent. Right? Because, you know, at least for many of us, we grew up with this kind of always in the background, right? And it's very, and like this kind of reasoning is scattered all throughout category theory as well. It's very difficult to untangle category theory from this sort of thing as well. So, but we've made considerable progress, and I am happy. I'm happy to say that I think we're at the point where, you know, once we had these insights, the rest of it is relatively straightforward. So anyway, so that's all I wanted to say today. Any other questions before we sign off? I can yield back 18 minutes.
I can only say that this is very abstract.
It shouldn't be, right? Because all we're talking about is, you know, this are sentences. Think about these as assertions about some data structure that you've coded up. So these are properties that you want the tester to verify against your data structure. Think about it this, you've done an implementation of sets and you hand this to your tester and they go use these things to try to break your implementation of sets.
Mm-hmm.
All right. So it's just, that's all that's going on. And so, but instead of implementing sets, let's say you implemented linear sets where, you know, for every element in the set, there was a corresponding, for every, how do I say this? For every way that you think about the set as really an interface between a client and a server, right? And so for every element the server has recorded, there's a corresponding delivery of that element that the client made. And for every element that the client has recorded, there's a corresponding delivery of that element the server made, right? So the data structure is like a ledger or a balance sheet, right? So if you implement that kind of balance sheet data structure, then you would have a corresponding set of axioms that are properties that nail down or pin down that data structure that you would hand to a tester to make sure that your data structure works properly. So
And,
go ahead.
I'm just thinking, you said this can be for example, the rolling, and these axioms are something like semantics of rolling. So if someone implement the rolling with the multiset, we can check if the implementation.
Close, very close. So what we're saying is, what I said was Rolang terms. So I didn't say that they necessarily had any operational semantics. Just the structure of the Rolang terms. This is just a data structure, right?
I see.
If you could make it be a data structure that wiggles, right? Right. So Rolang terms are sufficient to give you JSON, and JSON is sufficient to give you Rolang terms. So you could imagine that your data structure is a JSON gadget, right? And so and then over here you would have the bit of namespace logic that allows you to pin down exactly what is a JSON gadget. And then the tester is going to use these to make sure that your JSON implementation is correct. So it's not abstract at all. Well, what we're doing is demystifying and unabstracting math.
Oh, I see.
Yeah. Okay. Thank you so much. I'll see many of you in the dev stand-up.
Thank you, Greg.
Thank you. Bye-bye.
Ciao.